Next, we're going to talk about limits. Now, limits truly mark the beginning of our calculus study. Everything up to this point was a review of some of the algebra and trigonometry we could see as we do our calculus. But limits are the beginning of calculus. And for the rest of the semester, the three major topics will be something called limits, something called derivatives, something called integrals. And derivatives and integrals are both results, applications of limits. So let's start by talking about limits. We'll define a limit and then use this definition in some graphs to get a graphical understanding of the limit. So definition, let f of x be defined near a. We'll talk, in going through these graphs, we'll explain a little more about this definition in case the first read through is not terribly clear. Let f of x be defined near a. Let L be a real number. If all values of f of x approach L as the values of x approach a, then we say the limit of f of x as x approaches a is L, and we write this notation, lim with an x arrow a underneath it of f of x equals L. So the definition of a limit here says if all values of f of x approach some number L as x values approach a. So right here we're looking at the x and y axes. If on the y-axis the function approaches L, as on the x-axis x values approach a, then the limit as x approaches a is L. The limit of f of x as x approaches a is L. So let's look at this example. Well, let's look at these three examples actually. First, we have this one. So here's a function. I marked off the point 3,4 on this function because that's the 3 is the a value we're going to be looking at, 4 is the L value we're going to look at. So let's see what the limit, here we're going to look for, so let's say here, we're going to look at the limit of f of x as x approaches 3. So we're looking at the function as x approaches 3. So if all values of f of x approach L as the values of x approach, in this case, 3. Well, how many ways can x values approach 3? Well, we can approach 3 like that, or we can approach 3 like that. We can approach 3 from one side of 3, we can approach 3 from the other side of 3. So if values of f of x approach some number, as we approach 3 here and here, then we'll say the limit is whatever that number is. So what does the function do as we approach 3 from over here? Well, let's look at the function. The function goes like this. It approaches, in this case, function value of 4. And if we approach 3 over here, well, the function, the piece of the function that corresponds to is up here, and that also approaches 4. So in this graph, all values of f of x are approaching 4 as the values of x approach 3. So the limit as x approaches 3 is 4. Let's look at this next example. Again, we have the x value 3 marked off. That's what we're going to look at here. And again, we're going to look at approaching 3. And again, we can approach 3 in two different ways. What does the function approach as x approaches 3? Well, let's look at what the function is doing. I should go on this side so these look more shaded in. So this function, as you look at this side of 3, as you take this means of approaching 3, approaches that open dot at 4. On the other side, the function again approaches that open dot at 4. So here, we're looking at what the function does as x approaches 3. All function values as x approaches 3 are approaching this number 4. So here we say the limit as x approaches 3 of f of x equals 4. Now, you'll notice in here that says even though. So you'll notice here f of 3 is not 4. F of 3 is up here. F of 3 is 6. In this first example, f of 3 equaled 4. But down here, f of 3 equals 6, and the limit as x approaches 3 is 4. So let's look at this definition. All values of f of x approach L as the values of x approach, in this case, 3. Well, we're not looking, in this definition, we're not looking at what happens at 3. What happens at 3 doesn't even matter. All that matters is what happens as the values of x approach, in this case, 3. What happens at 3 does not matter as far as the limit is concerned. The function doesn't even have to be defined at 3. I could have gotten rid of that dot up there, and the limit would still be 4. So right here, this first part, let f of x be defined near, in this case 3. Near just means close to 3. It means near, the normal word near. But it does not have to be defined at 3. And next week when we talk about vertical asymptotes, we'll see functions that aren't defined at a value, but we can still describe their limits. So down here, the limit is 4 as x approaches 3 because the function approaches 4 as x approaches 3. Let's look at this next example. So this function is defined in 2 pieces, and in this case we're going to look at the limit as x approaches 2. We're looking at the limit as x approaches 2. Well, again, we can approach 2 in a couple different ways. We can approach 2 over here from that side. We can approach 2 from this side. And what does the function do as x approaches 2 on each side? Well, on this side, the function approaches this open dot at 3. Great. So if on this side we also get that the function approaches 3, then the limit will be 3. But notice, on this side, the function approaches that closed dot up there at 5. So let's look at the definition. All values of f of x approach L as the values of x approach A. Well, as the values of x approach 2, all values of this function do not approach the same y value. When that happens, the limit, we say the limit does not exist. So I'll say limit. Here, the limit does not exist. It doesn't exist because all values of x do not approach the same y value as x approaches 2. This way of approaching 2, the y values approach 3. This way of approaching 2, the y values approach 5. And because of an example like this one, we'll find this definition and terminology useful. So definition, we write limit as, well, we write lim, x approaches A with a superscript with a plus sign as a superscript. So here we write that notation, the same limit notation, but with a plus sign superscript on A. And we say the limit of f of x as x approaches A from the right is L. So here, this plus sign on the as a superscript of A says, look at the right of A. Look on this side of A. Look on this side of 3 in that case, 2 in this case. So the limit of f of x as x approaches A from the right is L. If the values of f of x approach L for x values approaching A with x, that should say greater than A. My bad. I must have been looking at the other one when I copied these from my notes. Or maybe I got it wrong in my notes. values of f of x approach L for x values approaching a with x larger than a. So we're looking at x values larger than a approaching a. So we're looking at x values larger than 2 for this first definition. Let's see. No, I just miswrote my notes. Good thing I read them when I'm writing them. Well, good thing I read them when I'm teaching. So we have the limit as x approaches a from the right, and similarly, there's a limit as x approaches a from the left with a negative sign as the superscript. So that's with left and with x values smaller than a. So we can find both of those limits in all three of these examples. In these first two examples, the limit as x approaches a from the right and from the left will both be 4. And you can see that with those arrows. But here, let's illustrate this definition with this example, or in this example. So here, I should say here, comma, not just here. We should use proper grammar. So here, the limit as x approaches 2 from the right. Well, what happens on the right of 2? Well, on the right of 2, values over here, as it approaches 2, the function approaches y value of 5. And on the left of 2, what happens? On the left of 2, so for these values, the function approaches y value of 3. Even though the function equals 5 at x equals 2, the limit doesn't care what happens at 2. The limit cares what happens near 2. And the limit on the right cares what happens on the right of 2. The limit from the left cares about what happens on the left of 2. And right here, in these first two examples, I said the limit as x approaches 3 from the right and from the left in each example was 4, which happened to equal this limit in each case. And here, we had different limits from the right and left, and the limit did not exist. And that generalizes to the following theorem. Theorem. Limit as x approaches a of f of x equals L if and only if the limit on the right equals L and the limit on the left equals L. Limit from the right equals L and the limit from the left equals L. So remember what if and only if means. If and only if means what's up here is exactly the same logically as what's down here. Meaning, this theorem actually says two statements. One, if we know that a limit is L, then we can conclude the limit from both sides must also equal L. And the one will probably, the direction of this theorem that we're more likely to use, and that we will use a few times, is if we want to show a limit is L, then we could show the limit from the right equals L and the limit from the left equals L. If we show the limit from the right and the limit from the left both equal L, then the limit will be L. And in those first two examples, that's kind of what we did, but we followed the definition of the limit. Let's look at before. So these limits have nice graphical interpretations. They also have convenient, very convenient algebraic interpretations. But before we talk about the algebraic interpretations, let's look at two more graphs. So let's take this graph. So here, f of x equals, let's say, 5. 5 is a good number. So y value of 5, here's f of x equals 5. And let's pick an x value. Let's just call it a. We don't need to. Let's just say a value is over there. So here, we want to look at the limit as x approaches a of this function. Well, as x approaches a, we'll use this theorem. We'll look at the limits from both sides, limits on both sides. On this side of a, function values approach 5. On this side of a, function values also approach 5. So the limit as x approaches a of f of x equals 5. And for this constant function, the specific constant we choose doesn't actually make a difference. So let's just say, I think I used the letter C in the notes. Yeah, I used the letter C in the notes. So if this function were any constant function, lowercase c, any constant function is still a horizontal line, the limit as x approaches a for any value of a. This a value could be here, it could be over here, it could be a equals 0. But for any a value, the limit as x approaches a of this function is that constant c. Let's look at this example now. F of x equals x. So the line with slope 1, y-intercept 0. And let's look at the limit as x approaches 4. How about? So 4 goes up here. What's that function value? Well, it's also 4. So here, we want the limit as x approaches 4 of this function. Well, again, let's look at what happens on the left of 4 and on the right of 4. On the left of 4, the function approaches that ordered pair at 4, 4. So the y value approaches 4 from the left. From the right, the y value also approaches 4. So here, the limit as x approaches 4 of f of x equals 4. And this value 4, what would happen if we chose any other number? Well, we would still have the ordered pair, that number, and that number. So if I just changed this to, I think I chose A. Yes. If I changed this to A, and this to A, well, instead we'd be looking at the limit as x approaches A of f of x, and it would equal a, where a is any number there. So for the constant function, any limit we have is that constant. For this function, an identity function you could call it, but for the function f of x equals x, the limit as x approaches a of x would equal a. And these two graphs give us two algebraic limit laws. And there are 7 algebraic limit laws. I'm not going to write them down because I posted this on Canvas in a separate document in week 2 called Algebraic Limit Laws. So if you could pull that up, then I will talk about these. There are 7. Let f and g be functions of x. C is a constant. First, limit as x approaches a of a constant. Well, that's what this says. F of x equals a constant. So the first one, I guess that's a different color. It's okay. Limit as x approaches a of a constant is that constant from a graph like this. The second one, limit as x approaches a of just x, because here the function is x. Limit as x approaches a of x is a. Now next, rule 3. The limit of a sum or difference of functions. So if you have two things added together and you're taking their limits, you could do them one at a time. So limit as x approaches a of f plus or minus g is limit as x approaches a of f plus or minus limit as x approaches a of g. Number 4, the limit of a constant times a function. So the fourth rule is very convenient. The limit of a constant times a function, well, so if you have a number in front of your function and you need the limit, well, you can pull that number out and then just deal with the rest of the function. Number 5 and 6, the limit of a product and the limit of a quotient is the product of the limit, is the quotient of the limit. We will see that that's convenient now, but in week 5, I guess, we'll see that a parallel result does not hold for derivatives, while parallel results for numbers 3 and 4 do hold. So here, if we have the limit of a product or the limit of a quotient, we can separate the product and the quotient and do the limit of each piece. And last, the limit as x approaches a of a function raised to some power equals the limit of the function all raised to the power. So if you have an exponent, you can push the limit inside the exponent and then take the exponent later. So let's now do a few examples where we apply these laws directly. And then we will summarize these laws. I want the black marker. So let's do a couple examples. Let's do, how many examples? Let's do 2 examples. Limit as x approaches 2 of x squared minus 5x plus 3. Now, you could graph this using a completing the square and then use a graph to figure out the limit. But I would guess that the algebra will be easier. So I'm going to do it using the algebraic limit laws. So what do we have? We have here 3 things added together. So we can apply rule 3 and split this limit into 3 limits. X approaches 2 of x squared minus, we're going to take that minus and apply rule 3, minus limit as x approaches 2 of 5x plus limit as x approaches 2 of 3. So we applied rule 3 and we broke this limit into 3 pieces. Well, now what can we do? Well, we have 3 limits. Seemingly is more complicated now. But we will follow these rules and see that we can use those rules to find each limit. So first, what is this function? This function is a function squared. So let's go back to the list of limit laws. Where is it? Right here. Let's go back to the list of limit laws. Do we have anything with functions squared? Well, rule 7. So I'm going to apply rule 7. There are going to be 3 different rules applied here, so I'm just going to write them stacked above the equal sign. Rule 7 says limit of a function squared equals the limit all squared. We can push the limit inside the square. How about the next one? Well, we have 5x. Do we have a rule that tells us how we can deal with a constant times an x? Well, yes, rule 4. Rule 4 says we can take that constant out and then multiply by the limit as x approaches 2 of x. And how about limit as x approaches 2 of 3? Well, how does 3 change as x approaches 2? As x changes, 3 doesn't change. So that limit is 3. Alternatively, you could have applied rule 1, which tells us how to take the limit of a constant. The limit of a constant is that constant. Well, that's great. Now we still have a couple limits to deal with. We have this limit and that limit, but both of them, notice, we need to find the limit as x approaches 2 of just x. And for that one, we can use rule 2. As x approaches 2, x approaches 2 by rule 2. As x approaches 2 here, x approaches 2. And the negative 5 carries through. And then we have a plus 3. And now we just combine these numbers, so you get 4 plus 3 minus 10. So that's negative 3. So this limit is negative 3. And then you check your answer to make sure that you didn't do something wrong. And that is correct. So here we applied, well, we applied 5 different limit laws. Let's do another example. Let's do, applying the product and the quotient feel pretty much the same. So let's do one with a product and see how that goes. I should have erased this too. So next example. Limit as x approaches negative 3 of root x plus 4 times x plus 2. That sounds good. So right here, what is our function? Root x plus 4 times x plus 2. Well, first thing we notice is that it's a product of two things. That to compute the limit of a product, we can split it into the product of the limit. So times, I'm going to write this on the next board so it's all on one board. So we have limit as x approaches -3 of this product equals the product of those limits. Well, now what can we do? Well, we have two limits to deal with, but the first one, which rule did we use here? We used rule 5 to get that first equal sign. How about this next one? Well, we have a function all raised to the 1/2. So we can apply rule 7 and push this limit inside that exponent of 1/2. And what can we do over here? Well, we have a sum. So we can do the limit by splitting it into the one thing plus the other, the one limit plus the other limit. So we have x plus 2 there. We need to multiply. Well, so this limit equals the limit of the first thing plus the limit of the second thing. And notice we're multiplying by that entire limit, so we need to multiply by this entire thing. Well, how do we proceed from here? Oh, what rule did we use for that? We used rule 3 for that second piece. We split a sum. Now, what can we do in here? Well, before even dealing with this 1/2, we have a limit of a sum on the inside. So we can again apply rule 3 to take the limit of the sum. And again, this is all still raised to the 1/2. So all we did here was split the sum into the sum of the limits. And what can we do now? That's a multiply. What can we do now over here? Well, we can apply, we have the limit as x approaches -3 of x. We can apply rule 2 to that. So rule 2, the limit as x approaches -3 of x is just -3. And over here, the limit as x approaches -3 of 2 is just 2 by rule 1. And now what do we have? Well, again, inside here we can apply rule 2 and rule 1. In here, we would get a -3. In here, we would get a 4. And it's still raised to the 1/2. We haven't dealt with that 1/2 yet. So in here, apply rule 2, apply rule 1, and then -3 plus 2 just adds to -1. So what do we have here with these numbers? So we have 1 to the 1/2 times -1. So that's -1. Now, a quotient is handled similarly. But let's look at these last two examples. What did we actually do, or what did applying those limit laws allow us to do? Notice, those limit laws eventually got us to a point where we could substitute x equals 3 into our function. In this one, we substituted when applying technically rules 2 and 1. So here, we substituted -3 for x. Down here, we did the same. For 2 and 4, you also technically substituted -3. You substitute -3 in for 2, you still have 2. And similarly for 4. So these limit laws, as we saw in these two examples, these limit laws allow us to use algebra to compute limits. And in particular, they allow us to interpret many limits through a direct substitution. So if you look up here, just immediately do a direct substitution. X equals -3. You get root 1 times -1, which is -1. And similarly for the previous problem, if you substituted x equals 2, you would get 2 squared minus 10 plus 3, which is what we had at the end. So the following theorem will allow us to, it'll consolidate these limit laws in a convenient algebraic way. theorem. For general f of x and g of x, upon direct substitution, the limit of the quotient, so limit as x approaches a, f of x over g of x, takes one of the following forms. And by upon direct substitution, we mean substituting x equals a. So really what it could say is f of a over g of a takes one of the following forms. And here we're going to use the pound sign for a non-zero number. So here it means a non-zero number. Any number, as long as it's not 0. We'll use 0 for 0. So it could take one of the following 4 forms. First, 0 over a non-zero number. Second, non-zero number over non-zero number. And in both of those cases, that fraction will be a limit. In case 1, 0 divided by a non-zero number is 0. In case 2, number divided by number, reduce that fraction, and that gives you the limit. And it gives you the limit by applying the algebraic limit laws. Case 3, if you do a direct substitution, you could get a 0 over a 0. If you get a 0 over 0 upon direct substitution, then what we will do is some algebra until the 0 over 0 goes away. And we'll see what I mean by that when we do, well, 3 of the examples. Not these 3, 2 of the, or 1 of these 3. Or also, upon direct substitution, you could get case 4, where you get a non-zero number over a 0. In this case, the function will have a vertical asymptote of x equals a. And we're going to talk about vertical asymptotes in week 3. So that the analysis of case 4, we're going to push off until week 3. But for now, let's look at these first 3 cases. Where's the blue marker? We're fine. Let's look at these first 3 cases. We're going to do 5 limits. 3 are written, 3 are not yet. So let's do this limit first. Limit as x approaches negative 3 of x plus 3 over x minus 3. This theorem, now this theorem is not explicitly stated in the textbook. I'm not positive why. I can only guess. But I think it's a convenient summary of many results. But this theorem tells us our first step should always be to try a direct substitution. Because if we do try a direct substitution and we wind up in case 1 or 2, well then we're basically done. If we do a direct substitution and it tells us we're in case 3, well at least we're not done. We're not done, but at least it tells us that we have to do some algebra. And similarly, if it winds up in case 4, well, it actually tells us a good deal if we wind up in case 4, but we'll see that next week. So let's try a direct substitution first, and I'm going to try it as side work up here. So let's do this first limit. The limit as x approaches negative 3, x plus 3 over x minus 3. Well, do a direct substitution. What do you get? You get negative 3 plus 3 over negative 3 minus 3. That's a lot of 3's. What does that equal? That equals 0 over negative 6. Well, 0 over negative 6 reduces to 0. We substituted and we wound up being in case 1. And we got a limit, or we got an answer of 0. So in case 1, that simplified fraction, 0, is the limit. So here, we had our side work, but it gave us a number. So in particular, that told us the limit was 0. And here, we wound up in case 1. How about this second one? Well, again, we have a limit. Let's try a direct substitution, and let's hope it works. Direct substitution, 4 times 9 minus 9 plus 2 on top, and we have 3 minus 7 on the bottom. So what do we get here? 36 minus 9 is 27, plus 2 is 29, over negative 4. I don't like writing fractions like that, so I'm just going to put the negative out front like that. So here we did a direct substitution. We got a number over a number. We got a number over a number. And by that theorem, case 2, when we get a number over a number, that reduced fraction is the limit. Well, that was nice. We did 2 limits essentially the same way. Let's try this next one. Again, we're going to try a direct substitution. you do a direct substitution, what do you get? You get 4 minus 2 all over 4 plus 2 minus 6. Well, what does that equal? 0 over 0. Well, 0 divided by 0 is not a number. But we use direct substitution, and now we know we're in case 3. So we're going to have to do some algebra until the 0 over 0 goes away. We're going to see 3 different types of algebra we could use. This will be one of them. So here we get a 0 over 0. So that tells us we need to do some algebra. Actually, I might not be able, or I might be able to fit it on these boards now. What algebra can we do? Well, we have 2 degree 2 polynomials. Do they factor? Well, yes, they do. How do they factor? Well, on top we have an x minus 2 and an x plus 1. Because negative 2 and 1 make negative 2, negative 2 and 1 make negative 1. On the bottom, we have an x minus 2 and an x plus 3. Because 2 and 3 make negative 6, 2 and 3 make 1. Well, that's great. We factored. Is this going to help us at all? Well, let's look at this fraction. This fraction has the same thing on top as it does on the bottom. When that happens, they simplify to 1, those 2 pieces. Something divided by itself is 1. So right here, this limit now equals this limit. Because the fraction reduced. And what happens with this limit? Well, we have a seemingly new limit. We can apply this theorem, meaning we can try a direct substitution and see if that helps us. What happens if you do a direct substitution here? Well, you get 2 plus 1 on top, and you get 2 plus 3 on the bottom. So what does that equal? 3 over 5. 3 over 5 is a number. We're in case 2. So that limit equals 3/5, but that limit also equals the original limit. So the original limit equals 3/5 as well. So in that third example we did, we used factoring to simplify, in this case, a rational function. And in simplifying it, it allowed us to cancel this. Now, how does that follow from what I wrote in this theorem? In the theorem I just erased, but I wrote, do algebra until the 0 over 0 goes away. Well, that's mathematically imprecise language. But what we really did was we did some algebra that allowed terms which, upon substitution, gave us our zeros. You substitute x equals 2 in each of these, you get, in each of those things we cancel, we get 0. Now, the question is, did we say in that step that 0 divided by 0 is 0? In going from steps 2 to 3, did we say that 0 divided by 0 was 0? Excuse me, 0 divided by 0 is 1. Did we say that? Well, let me write the next question while you ponder. Did we say 0 divided by 0? I'm going to tell you right now. 0 divided by 0 is not 1. 0 divided by 0 is not defined. So did we use a fact, in quotes, that 0 divided by 0 is 1? Well, the answer is no, we didn't. Why didn't we? Well, we're taking a limit. The limit does not care what happens, in this case, when x equals 2. When x equals 2, that gives us a 0 over 0. But what happens at 2 doesn't matter. All that matters is what happens close to 2. And for x values close to 2, this fraction always reduces to 1. At 2, it doesn't reduce to 1. But close to 2, it does. And the limit does not care what happens at 2. So we did not say 0 divided by 0 is 1. Let's look at this next limit. Well, we have another limit. That theorem tells us we can try a direct substitution and hope it works. In these first three examples, the direct substitution ones, examples 1 and 2, were much shorter. Well, they required much less work than example 3. So if a direct substitution works, that's quite convenient. So does a direct substitution work here? Well, try it. Direct substitution gives you that. Root 9 is 3 minus 3 over negative 4 plus 4 equals 0 over 0. Well, we got 0 over 0. So that did not give us a number. But it did tell us that we can do some algebra. Well, it suggests that we can do some algebra. And in this case, there is some algebra we can do. Now, in the first example, we did factoring. And that allowed x minus 2's to show up. Here, well, I don't know how to factor that top. I don't even know if it can be factored. Well, it can be sort of factored. But I don't know how it can be. But one thing we can do is multiply by a convenient 1. If we multiply by a convenient 1, well, if we multiply by any 1, it's not going to change the original limit. But if we multiply by a convenient 1, it will allow us to simplify the numerator in a convenient way. Now, which 1 will we multiply by? This 1. Well, that's not multiplying by 1. But if we multiply the numerator by that, we can apply the difference of squares result, which says something minus something. So notice in this numerator, all we did was change that negative sign to a positive sign. We can use on the numerator the observation that something plus something times something minus something is the first thing squared minus the second thing squared. And we'll see that that will allow this to simplify. But what's written now changes the question, so we can't change a question. So if we multiply by something, we have to also divide by that thing. So right here, we are multiplying by 1. And we will see that that allows this limit to simplify. And all we did was look at the square rooted term and change the sign between the square rooted term and the other term. And we will apply the difference of squares. So multiply these out. What do we get? Well, on the bottom, you don't have to, well, on the bottom, multiplying everything out will make it harder to see. So we won't multiply any of the bottom out. We'll just leave it as it's, we'll just leave it as the one thing times the other thing. But what happens in the numerator? Well, this happens in the numerator. X plus 13 minus 9. Why does that happen? Well, the difference of squares. A minus b times a plus b is a squared minus b squared. A squared, square root squared, is itself, so x plus 13. 3 squared is 9. And we subtract them. So in the numerator, we have x plus 13 minus 9. Well, that's great. What do we have now? Well, sometimes these take a lot of writing, and sometimes I skip over this next step, but for the first example, I'll write this next step. That numerator, what does that simplify to? Well, 13 minus 9 is 4, so we have just x plus 4 on top, and again, we'll leave the bottom alone. But now, look at what we have. We can't do a direct substitution yet. We'd still get a 0 over 0. But look at what we have. We have an x plus 4 on top and an x plus 4 on the bottom. So close to negative 4, they will cancel to 1. And that limit now equals this limit. We still haven't taken a limit yet. We can't get rid of limit as x approaches -4 until we've actually taken a limit. And we haven't taken a limit, we just did some algebra. But now we will try a substitution. We get what? -4 plus 13 under a square root plus 3, 1 over 3 plus 3. So we get a limit of 1/6. And notice here, in going from there to there, we did do a direct substitution by applying the previous theorem. Or we did, we did take the limit by applying the previous theorem. So the limit went away. The limit notation went away. So here we have an example where the 0 over 0 took a different form, and we canceled the 0 over 0 using another kind of algebra. And we leveraged the difference of squares result. Let's do one more limit. Let's open our marker so we can actually write with it. Limit as x approaches 1 of, yeah, okay, this will fit on this board. So limit as x approaches 1 of 1 over x plus 1 minus 1/2 all over x minus 1. So here we have a 3-tiered fraction. But again, we can try a direct substitution. What happens if we do a direct substitution? Well, in the numerator, you get 1/2 minus 1/2. In the denominator, you get 1 minus 1. 1/2 minus 1/2 is 0. 1 minus 1 is 0. So we get a 0 over 0. And here, we'd like to get rid of that 0 over 0 we'd like to apply case 3 and get rid of 0 over 0. How can we do that? Well, we have all these fractions. Let's just try to reorganize this so it's one fraction. How can we do that? Well, we can do it like this. Whenever I have a 3-tiered fraction, I always like to exaggerate the overall fraction bar just to help keep me organized. So we have this 3-tiered fraction. The real nuisance is on the overall numerator. So before even dealing with the denominator, I'm just going to work on the numerator. So I'll leave the denominator as it is. Now what can we do in the numerator? Well, we can combine the fractions by finding a common denominator. The common denominator in the numerator is the 1 times the other, so 2 times x plus 1. To get that common denominator in this first piece, we need a 2. So 2 times 1 is 2. To get that common denominator on the second piece, we need an x plus 1. So multiply by an x plus 1. So you get 2 over 2 times x plus 1 minus x plus 1 over 2 times x plus 1. Combine the fractions, you get 2 minus, don't forget the negative sign, all of x plus 1, all over 2 times x plus 1. And then that entire fraction is all over x minus 1. You could have also done the cross-multiplying way of combining fractions, which I find much easier to think about. Cross-multiplying way would be 2 minus 1 times x plus 1, so x plus 1, all over 2 times x plus 1. Or you could do the common denominator. I don't like the common denominator that much. I think it's too much thinking. But what can we do with this now? This doesn't look all that much simpler. That was not a well-formed sentence. This still does not look simple. Fact. But what can we do with it? Well, let's still leave that denominator as it is. Actually, let's not do that. Let's get rid of that denominator. How can we get rid of the denominator? Well, we're not getting rid of how can we simplify it? Well, we can remember the what? The fraction rule. Fraction divided by c is what? Multiplied by the reciprocal. Multiplied by the reciprocal of the bottom. The reciprocal of the bottom, 1 over x minus 1. So we get 2 minus x plus 1 all over 2 times x plus 1 times x minus 1. So all we did here was multiply by the reciprocal of the overall denominator. Well, did that help us? Well, it actually did help us if we also simplify this numerator. What does that numerator simplify to? Well, I'll do the side work over here. 2 minus x minus 1. So what is that? 1 minus x. 2 and negative 1 make 1. Negative x is negative x. Now, if we try a direct substitution here, we're again going to get a 0 over 0. But can we do a canceling? Well, we can, sort of. Look at this 1 minus x. That looks a lot like that x minus 1. Not entirely like it, but it does look a lot like it. How do those two terms differ? Well, in the top, there's a positive 1 and a negative x. In the bottom, there's a negative 1 and a positive x. So that means they differ by a negative. So we can, in the top, factor out a negative 1. Factor out a negative 1 from x, factor out a negative 1 from negative x, you have just x. Factor out a negative 1 from 1, you have a negative 1. And here, the x minus 1s will now cancel. And what do we get? Well, still haven't taken a limit. What do we get? On top we have a negative 1. On the bottom we have a 2 times x plus 1. And what do we get? Well, we can now do a direct substitution. Negative 1 over 2 times 2 gives us negative 1/4. So here, the algebra we did, we simplified the large fraction, and then that eventually allowed us to cancel our x minus 1 terms. Cancel the things causing the 0 over 0 upon direct substitution. So these limits, especially the case 3 limits, and you can see the real bulk of the work here was handling case 3. But these limits are very important, and we'll see them, well, we'll see them indirectly throughout the semester. We'll see them directly through week 4.